All right, 5.5, first differences. What's really important here in first differences is to understand how a linear relation starts. Now, when the finite differences, i.e. first differences, are a constant value in the first part, then the relation is linear. If they are not a constant value, then the relation is nonlinear. So at this point in time, in the first time you learn about finite differences, we only look at the first differences. Now we're going to look at some examples that refer to how to define whether something is linear or not. Now, the above is conditional on the x values following a particular pattern. Now this is going to be important to note that before you even can look at the first, second, or any sort of finite difference, you must ensure that the x values follow a specific pattern. We're going to look at that specifically in the examples that follow. If the x values do not follow a pattern, then you must say that the relation that you're given is unable to be determined. It's unable to be determined because the x values do not follow a specific pattern. Now, the constant of variation can be determined only when the relative relation is linear. A constant of variation is also known as rate of change, which is also known as slope. So, slope, we've learned, is delta y over delta x, or we will use this concept in this unit. We've learned about slope as the letter m. We've learned that slope is rate of change. We've learned how to calculate slope with 2 points. And now we've looked at seeing that a constant of variation is known as slope. A constant of variation is a change in the y over the change in the x. And we're going to look at that a little bit in the next set of examples. So this delta is a Greek letter that represents change in the y values. How do the y values change? Over delta x, delta represents again change, but this time it's the change in the x. And this is important to learn in grade 9 because it's going to become a familiar topic that is discussed in later years. Now let's look at some examples. Example 1. Determine the type of relation. So I'm going to give you a table of values as such, and what you're to do is determine the type of relation. The first thing you should do for all tables is ensure that the x's go in a pattern. You see the x's are in order, and now that we've seen that the x's are in order, we can now perform the delta x. Delta x, what we are checking here is that the x's actually follow a pattern. So the first thing we look for is that they are in order, and the second thing we look for is that the x's follow a pattern. That is, from 0 to 1, we're adding 1. 1 to 2, we're adding 1. 2 to 3, add 1. 3 to 4, add 1. 4 to 5, add 1. Notice, folks, that all of these result in the exact same value. So all of the values in delta x are the same. Then, that is like giving us permission. Permission to now go and explore the y values. Because if the x's follow a pattern, we need to see if the y's follow a pattern. If they do not, then we have to result in the answer. If they do, we have another answer to say. But right now, we see that the x's follow a pattern. That is our permission to now go and do the delta y. Delta y is up to, up to, up to, up to, up to. Wow! So we see that the delta y's also follow a pattern, and all these numbers under delta y are the same. Now, if this was a word here like time, you would write delta time. If this is like distance, you would write delta distance. It's very important that you write the delta according to whatever is in this column. Now, note that we have both the same. Well, because delta y x and delta y is the same, we can make a conclusion. What's our conclusion? Well, therefore, the relation is linear. It is linear because delta x and delta y are the same. All right, moving on to another example. Example 2, or part B. So here is our next table. Whoops, that's too much, folks. Let's go backwards a bit. So here's our table. And what does our table do? Well, we need to see that the x's go in order, which they do. And now what we're going to look at is, do the x's follow a pattern? Let's see. Delta x, up 3, up 3, up 3, up 3, up 3, and up 3. Well, yes, that's right, folks. Delta x values are the same. Now we go over to delta y. What's happening with delta y? 9 to 4 is minus 5. 4 to 1 is minus 3. 1 to 0 is minus 1. 0 to 1 is plus 1, plus 3, and plus 5. Wait a minute. These numbers look like they were following a pattern, but when we did the delta y, we noticed they are not the same. So these values are all different. Because the x's are the same and the delta y's are not the same, we can say the following. We can make the following conclusion. Because delta x is the same and delta y is different, we can make a therefore conclusion that the relation is nonlinear. That's right, nonlinear, because these numbers do not follow a pattern, i.e., these numbers are not the same. Delta y is not the same, and delta x is, so it's non-linear. Moving on, let's try another one. Here's another table with all these values, and we check to see that the x's are going in order, and they are. Now we go and do our delta. Delta x, so the numbers are going up 4, down 4, down 4, down 4, down 3. And because it's going down 4, down 4, down 4, down 3, and then down 4, down 4, down 4, down 4, just like this, folks, we notice that the delta x's are different. And it doesn't matter what's going on in the y's. Because the delta x's are different, folks, we need to make the following statement. And that is, because delta x is different, we are unable to determine the type of relation. It's unable to determine the relation because delta x is different. Okay, moving on to another example. Let's look at this table. We have a table of values right here. And these are larger numbers, of course. And we need to see that the x's go in order. Yes, they do. And now we're going to perform our delta. Delta x, minus 2, minus 2, minus 2, minus 2, minus 2, and minus 2. And we see that delta x is the same. Wonderful. We move over to the other side, delta y, and we see that delta y, okay. Now, let's say we had distance up here. We would write and height. Remember what I mentioned earlier. If we had distance and height up at the top of the table, we would write delta distance and delta height. Be careful and make sure you write the corresponding correct values for the deltas. Now, let's go back to the table. we notice that 189 to 193 is up 4. And again, up 4. And again, up 4. And again, up 4. And again, up 4. And finally, oh yes, that's right, up 4. So all of these values are the same. So what can we say about this type of relation? You guessed it. Therefore, the relation is linear because delta x and delta y are the same. All right, let's look at one more example. Here it is. You should notice right away that there's something wackadoodle about it. What is? Well, notice that the x's aren't even following a pattern. That's right. We need to put this in order. So we're going to start. Delta x and y, not even delta, folks. We're just putting it in order. That is, we start with the lowest x, which is -7, or we could even start with the highest x if you wanted and go downwards. Doesn't matter whether we start with the highest or lowest, but we have to start with one n. So I start with -7 being the lowest. And with that comes 12. So -7 and 12 goes together. Next, we will do the next number that's in order, and that would be -5. So -5 and 15 goes together. Next comes -3. -3 and 18 go together. Next, -1. -1 and 21 go together. And finally, 1 and 24. So now that we've put the x's in order and their corresponding y's, we can now determine delta x. Delta x is +2, +2, +2, +2. So these values are all the same. Now we have to go to delta y because now we've been given permission to go to delta y. Delta y says the values are +3, +3, +3, and again +3. Yay for us, because the delta x and delta y values are the same, we can say that this relation is in fact linear. And that is because the delta x and delta y values are the same. Okay, one more example page. Folks, here we go. Example 2. Determine the rate of change from all the linear relations in example 1. Well, so from example 1, we found out that A was linear. So how do we find the rate of change? Remember that rate of change means constant of variation. Constant of variation means slope. So what essentially we're doing is finding the slope of each of the lines in example 1. All right, so let's look back at example 1. Here is example 1, and we see that our delta x was +1 and our delta y was +2. What we need to do is use that to determine the slope of this particular linear relation. All right, let's go back to the example 2 page. So we need to we knew that A was linear, and we know that slope, m, is equal to delta y over delta x. So what were our values for delta y? Well, delta y was 2. Whoops, wait a minute, folks. We'll just zoom a little bit back. Here we go. Delta y over delta x is equal to 2 over 1. That is, delta y was 2 in example 1, and delta x was 1. 2 over 1 reduces itself to just 2. So we've simplified and found the slope, or rate of change, or even constant of variation for the table in example 1a. Next, we look at example B. Let's go back and look at B from the previous example. Here we go. Here is B, and we notice that it wasn't linear. Let's look at C. C was not linear either. So we couldn't look at C or B. And finally, let's look at D. What was D? D was linear. Because it's linear, we note the delta x, we note the delta y to determine the slope. Let's go back to example 2. Here we go. B was not linear, C was not linear, but D was. So we need to find the slope. Slope is equal to delta y over delta x. Delta y in example 1D was positive 4. Delta x was negative 2. 4 over negative 2 reduced is negative 2. So our slope for D was negative 2. What about example E? Do you remember if it was linear? That's right, it was. Example E was linear. Let's look back at example E. Example E, we had to put in order, and once we put it in order, we found out that delta x were the same and delta y was the same. So example E was definitely linear. Let's determine the slope. Okay, for example E, we need to find the slope, delta y over delta x. Do you remember what delta y was? That's right, 3. 3 over delta x, which was 2. 3 over 2, folks, is reduced and is our final answer. So the slope of all the linear tables can be found by looking at the delta y over the delta x. Well, folks, that's the end of the video. Have a numerical day.